So now that we've covered all the tests on dealing with proportions, we can move on to a new metric, which is the average or the mean. When we're talking about a mean or an average, we're talking about a variable that is quantitative. Remember that a quantitative variable is one that has a units attached to it. So examples of averages might be the average level of monoxide, because that's measured in tons or particles per million. Maybe it's the average payoff in a game of craps, that would be measured in dollars, or even the average starting salary of an ISU student. Remember that the average is just the center point where we think the middle point of a distribution is. Now, typically, we don't know the true population of, let's say, all ISU graduates. It's difficult to go out and survey people after they've left ISU and ask them what their starting salary is. So instead of surveying the entire population, we'll just survey a sample of them. And what we're interested in is what repeated samples might look like. So that's called our sampling distribution. Remember, we dealt with sampling distributions before when we were dealing with proportions. Now we're dealing with them for the average. So what we're thinking about is repeated samples, let's say again, of ISU students, and we're thinking about what the average starting salary might be. Now, sometimes the average starting salary is going to be high, sometimes it's going to be low. There's going to be variation in our repeated samples. And so the distribution of those repeated samples, not surprisingly, is going to follow a normal model. The mean is going to be centered around what that true average of all ISU graduates. And then the samples are going to vary, and the way in which they vary depends upon the true population standards deviation, so the amount of variation there is in salaries. Also, how many people you're sampling. Remember, your sample size impacts how much your sampling distribution varies. So let's be really clear here, because we're dealing with two different distributions, and we want to make sure that we're dealing with the right one. So the difference between these two is that the first one deals with a sample. So the distribution of a sample, you might create a histogram from. Let's say you go out and you survey 100 ISU graduates, ask them what their starting salary is. You can calculate an average from that, where you think the typical salary might be. Some people are going to make more, some people are going to make less. The standard deviation captures that variation in salaries. The second distribution is what's called a sampling distribution, and this is a theoretical distribution that focuses on the idea of repeated sampling. So instead of going and sampling once, you go out and you sample 100 people, but you sample, let's say, 2,000 times. Some of your sample averages are going to be higher than the true average, and some of your sample averages are going to be lower than the true average. So there's also a deviation in your repeated samples. Now, this theoretical distribution is what we're going to be using to run our tests. And that is what this formula demonstrates, this standard deviation of the repeated samples, the averages from those repeated samples, is going to be a function of the true standard deviation of the population and the sample size that you're pulling from. Now, this is a theoretical distribution that deals with the idea of repeated sampling. But typically, we only sample once. We don't sample repeatedly, or we don't even sample 2,000 times, because that's extremely costly. And that's what makes this a theoretical distribution, is that we can use these formulas to get an idea of where we think the true average might lie. So the kinds of questions we can ask looks like this, where we're given a standard or a claim, and we can go out and sample people or sample objects and try to test that claim. So here we have the claim that the average starting salary for ISU graduates is greater than $100,000. To test this, we can go survey a bunch of ISU students. Let's say we survey 150 of them, and that sample average we can create a distribution from and see if that sample average is statistically different or greater than 100,000. We could do that also for this claim that the average cholesterol level for a person with diabetes is 240. We could go out and we could survey 300 people with diabetes, test their cholesterol level, and then compare that sample to this claim. So let's go ahead and do that on a problem. Here I have the claim that ISU is better at math than the national average. Here we're given the national average. We're actually even given the state of Illinois' average of ACT math scores. In 2013, ISU's math scores were 23.7, and this was for new incoming students. So there were 4,782 new students at ISU that year. Their standard deviation, again, some students scored higher than 23.7, some scored less than that. The standard deviation captures that variation. So the null hypothesis in this claim is that we're going to assume that ISU's actual average is the same as the nation. Remember, what we're given here is just a sample of ISU students. That's 4,782 students. It's not all ISU students. The population average is what we don't know. So we're just going to say that it's the same as the nation, and the reason why we see a higher score for our sample is because samples vary. We're going to try to use this sample as evidence then that ISU is in fact greater than the nation. So we do this by creating what's called a t-score. So before, with proportions, we created a z-score. Now we're creating what's called a t-score, and it's going to follow a similar pattern. We're going to start with our sample first and subtract off our hypothesized value, which is what we put in the null hypothesis, and then divide by our standard error, or standard error. This is going to be based on the standard deviation of the population and the sample size. So this is just the formula, and I'm going to show you that formula in more detail in a second. When I calculate this t, I get 64.11. The other thing that I need is what's called the degrees of freedom. This is essentially how much information I have and accounts for the number of parameters that I'm trying to estimate, which is just one parameter. So I have 4,782 data points. That's how much information I have. So my degrees of freedom is 4,781. To get our p-value then, remember the goal of any test is to get a p-value so that we can compare it to an alpha level. We need to either use a TI calculator or Excel. There are some programs on the internet that do it as well, but for ease, let's focus on the calculator or your Excel. For the calculator, you're going to want to plug in into your TCDF function the following numbers. So this number here, 10 to the 99th, that's your essentially infinity. That's the largest number that the computer can hold. So it's like you're reaching up from 64.11 up into infinity, up as high as the computer will go, accounting for the degrees of freedom. That's what this calculates. I'm going to provide for you a document below on ReggieNet that shows you how to find the TCDF formula in your calculator, so you can just utilize that. When you enter it, it's going to be 0.00. The same formula is used in Excel, and the way that we calculate it is with this formula for t-dist. So the formula is 1 minus t-dist, and I actually have to put in the formula here. I would need to put in an equal sign before I entered all this so that the computer knows, or Excel knows, that I'm entering a formula. The three numbers here then are the t-score that I just calculated, my degrees of freedom, and then this last number just says, hey, we're trying to calculate the cumulative distribution function. We're just trying to find that area greater than 64.11. Now I say greater than because our alternative hypothesis was greater than. So we're just trying to look at everything above 64.11. Either of these two methods are doing that, and that's why I get the same probability. So because my p-value is so low, I can reject that null hypothesis. It's lower than any common alpha level that I could specify. So I'm going to reject that null hypothesis and say I have evidence in favor that ISU's average of ACT math scores is in fact greater than the national average. So good job, ISU students. So that was a lot of information. Let me try to break it down a little bit more so you can see each of the parts. The first thing that we did was set up a null and alternative hypothesis. The methods for that are similar to that of proportions. You need equality in the null hypothesis, and then if you have direction, that always goes in your alternative hypothesis. From that, we generate our t-score. It follows the same logic as that of a z-score, and I'm going to tell you how it's different from a z-score in a second. We put our sample observation first, and then we subtract off our hypothesized value. So this is the hypothesized average that we're focusing on. Our standard error then is where we think the distribution of averages would look like. It's going to account for the variation in the sample, but also the sample size. So S here represents the standard deviation of the sample, and the square root of n is just n is the number of people that we surveyed, so it is the sample size. The degrees of freedom, as I mentioned before, is just the amount of information that we have, and we're going to use that to help determine our p-value. Now, the t-distribution is slightly different from the normal model because what we're dealing with small sample sizes, and we're estimating a standard deviation. So that means that the t-distribution actually has fatter tails than the normal model. So if we use the normal model instead of the t-distribution, we're going to reject the null hypothesis more often than we actually is appropriate. So that's why we have to use the t-distribution. Now the t-distribution actually changes the more observations that we have. And that's again why more observations are better. The more observations you have, the closer this t-distribution starts to look like the normal model. But it also means that the distribution is different depending upon your sample sizes. If you have a small sample size, the difference between the t and the normal model is going to be quite large. But if you have a very large sample size, there's only going to be a small difference between the t model and the normal model. So why do we need this t-distribution? Well, the problem comes because of this standard deviation of our averages. The way the standard deviation of the average is calculated is generated using the standard deviation of the population. Now, typically, it's difficult to survey the whole population. That's why we're running these tests. If we could just survey the whole population, then we wouldn't need statistics. So oftentimes, we don't know what this population standard deviation is, and we have to use a sample estimate of it instead. So as you can see, we're using a standard error instead of a standard deviation. This creates more variation and more potential error in our model, into our test, and that's why the t-distribution is used rather than the normal model. Now, just to be clear, your book does go through some problems where we know the sample average and the true population standard deviation. When we don't know it, we use the standard error. So I'm going to focus on the problems where the population standard deviation is unknown. But again, the problem goes through some examples where the population standard deviation is known, and you can use a z-score for that. So just be aware when you're doing problems whether or not you know the true population standard deviation or not. So this is the formula for how you test a mean using one sample t-test. Now, feel free to refer back to this video after you've tried a few more problems. It may be useful because there's a lot of information all at once. In the next video, I'm going to go through another problem showing you how to run this test and again, how to calculate those p-values.